So, Assalamualaikum warahmatullahi wabarakatuh. My name is Nurali binti Muhammad Noor. So, today I will present you my research study, which is oviposition rate of Pseudophilus oryzae in Japonica and sticky rice. So, the outline for this presentation: introduction, literature review, research methodology, result and discussion, conclusion, recommendation, and also references. So, we are going to go through the first part, which is introduction. So, as you can see, S. oryzae is the major pest of stock product, and if you can see in figure 1, there is the image of Pseudophilus oryzae. They are locally known as the rice weevil and lesser green weevil in Malaysia, where we usually call it buk beras, kumbang beras, or kutu beras. So, the damages caused by this pest are various. Okay, now I will explain about this damage. The presence of S. oryzae result in contamination as they mold and excrete fecal matter, which result in diminishing the market value of commodities. The ongoing consumption of rice product by their increasing population further worsen the reduction in rice product quantity and quality of the rice. So, as you can see in figure 2, there is this is the damages caused by S. oryzae, where the rice grain has been continually fed and contaminated until it becomes dust. This is the significant loss of our rice in Malaysia. So next is problem statement. The intrinsic growth rate of S. oryzae within Japonica and sticky rice has not been investigated to date, and the study on the population growth and overpopulation rate of S. oryzae based on rice grain in Malaysia is still poor. And lastly, this knowledge gap will hamper the optimization of pest management, specifically in timing fumigation application. So, this is why it is important for us to understand the knowledge about this intrinsic growth rate, oviposition rate, and correlation between both information. Thus, we can aid in giving much better pest management program for rice industrial in Malaysia. So, the significance of study. When we discover the population growth rate, it allows us to relate to intrinsic growth rate and determine the oviposition rate of S. oryzae. These data can be used to determine the precise timing for fumigant application in industrial rice, and precisely timing fumigant application for rice grain would significantly improve industrial efficiency and ecological sustainability at the same time. So, providing this information will boost profit and minimize losses for the rice industry in Malaysia. And lastly, that's why our objective is, first, to determine the intrinsic growth rate of S. oryzae in Japonica and sticky rice, to determine the oviposition rate of S. oryzae in Japonica and sticky rice, and lastly, to relate the oviposition rate and population growth of S. oryzae in Japonica and sticky rice. Okay, next we are moving to the literature review, the second part. So as you can see in figure 3, this is the Sumo Calrose rice, represented Japonica rice. Sumo Calrose rice is a hybrid variety developed in California, USA by crossing a Japanese Calrose variety with high-yielding indica rice. And next, as you can see in figure 4, that is Jati Beras Pulut Thai, represented sticky rice, and it hails from Thailand. So the rice grain are short, round, and almost opaque. And then, so as you can see in table 1, table 1 shows the damages caused by S. oryzae. So first, it caused direct grain damage, then physical and microbial contamination, and then reduced quality and loss, and lastly is infestation spread in the rice grain. So next is the control of pest management. So for pest management, we are going to use the fumigant technique. So the fumigant used is methyl-bromide, which can destroy S. oryzae at all phases of its development. So here, fumigant, which is methyl-bromide, it will disrupt the S. oryzae respiration, causing neurotoxicity, metabolic disturbance, respiratory suppression, and growth distortion. So next is table 2 show population growth of S. oryzae. So the population growth, if we understand population growth of oryzae, we can know the reproduction and growth, which is rice weevil S. oryzae lay many eggs and leading to more offspring. So the life cycle of S. oryzae, it has 4 stages, which are eggs, larva, pupa, and adult, and it takes 28 days to complete one cycle of life cycle. So then is population size and competition. So the larger the S. oryzae population, compete for resources like food and spaces, and this competition can harm the individual growth and reduce egg production. And lastly is pest management technique. Acting early during the rapid growth phase is more effective than waiting for a steady population. So next we are going to move to the research methodology, which is our third part. So in order to obtain the population growth rate and oviposition rate, I first culture the S. oryzae in 266 petri dishes with pure grain from October to December 2023 under control conditions. Then, I did the rice grain matrix. 50 Japonica and sticky rice samples were measured for the size, which are length, width and perimeter using 0.01 mm microscope roller and image jet application. Then, moisture content analysis. 3 sets of 50 gram rice samples were initially weighed, dried at 130 degrees Celsius to 140 degrees Celsius for 24 hours using oven, and the moisture content was calculated. Then, in order to observe the population growth, I prepared 200 petri dishes. 1 S. oryzae adult with 120 rice grain were put in each petri dish, and in another 66 petri dishes, 10 adult of S. oryzae with the same rice quantity were also put in each petri dishes. So next, population growth rate of 20 selected samples. So 20 selected samples from 266 were analysed. So I counted S. oryzae until a consistent number was observed 4 times in a row. And lastly, to get the oviposition rate of S. oryzae, they were observed at 5 to 30 days with S. oryzae in petri dishes. Oviposition was identified using red dyed acid fuchsin acid, and the blackish red dot indicate the egg of S. oryzae in the rice grain. So lastly, I did the statistical analysis. The dataset applied a logistic growth model using Python Jupyter Notebook, assessed accuracy with MEDAPE and MASE matrix, and analyzed data. Analyze the correlation between oviposition and growth rate using XLStat. So next we are going to move to the fourth, which is result and discussion. So as you can see, table 3 show the intrinsic growth of S. oryzae on Japonica and sticky rice. So as you can see, sticky rice with 10 starter culture has highest growth rate, which is 0.20 compared to others. And as you can see, this is the result based on the population growth S. oryzae in sticky rice. The blue dot is the actual value, the orange dot is the predicted value that has been based on the simulated logistic growth model. From the result after we have been analysed using Python and Jupyter Notebook, we got the intrinsic growth rate for population growth was in sticky rice with 1 starter culture is 0.10, and sticky rice in 10 starter culture with 0.20. Next, for the population growth of S. oryzae in Japonica rice. So the intrinsic growth rate for the population growth in Japonica rice starter with 1 culture is 0.16 and 10 culture is 0.17. So the logistic growth model can be seen in equation 1. So using the formula in equation 1, the predicted value was calculated using this formula. So next is median absolute percentage error MEDAPE and mean absolute scale error MASE of S. oryzae. So as you can see, MEDAPE and sticky rice reduced from 8.39% to 2.64% as the number of S. oryzae grew, while MASE dropped from 0.06 to 0.22. And MEDAPE in Japonica rice dropped from 4.98% to 0.76% when the number of S. oryzae increased, while MASE decreased from 0.13 to 0.11. So this implied that sticky rice gained accuracy as the quantity of S. oryzae grew, yet the value were larger than Japonica. Japonica consistently produced lower result for MEDAPE and MASE, indicating greater accuracy than sticky rice. So next, oviposition rate of S. oryzae. Table 5 shows the oviposition rate of S. oryzae on Japonica and sticky rice. So as you can see, S. oryzae in sticky rice has the highest oviposition rate, which is 1.03 compared to Japonica rice, which only 0.43. So factor that affect oviposition rate and population growth rate of S. oryzae is for moisture content. Japonica has the moderately high moisture content, which is 60%. Compared to sticky rice, which is only 14.57%. For grain size, which is width, length and perimeter, sticky rice has larger grain size compared to Japonica rice, which lead to sticky rice has higher weight compared to Japonica rice. And next is correlation between oviposition rate and intrinsic growth rate. So, oviposition rate is negatively correlated with moisture content and width, and positively correlated with length and perimeter. Or before that, I will only explain the bold value, as the bold value is significant with 0.05. And for the intrinsic growth rate, it has negatively correlation with length and perimeter. So as a result, the positive correlation between oviposition rate and both length and perimeter indicate that large rice grain have more oviposition location or attract S. oryzae for egg laying. So this made perfect sense because larger grain will provide greater surface of S. oryzae to lay eggs. However, negative relationship between size which is length and perimeter and intrinsic growth rate may indicate that larger grains were less successful in creating succeeding generation. So a study by Majmarani et al. In 2023 showed intrinsic growth rate of S. oryzae in sticky rice overlap with rush rice, which has intrinsic growth rate at 0.043. A study by Majmarani et al. In 2023 showed intrinsic growth rate of S. oryzae in Japonica rice different with Hashemi rice, which has intrinsic growth rate of 0.067. So to conclude, sticky rice showed a higher intrinsic growth rate, which is 0.20 compared to Japonica rice, which is only 0.17. Lastly, sticky rice had the highest oviposition rate, which is 1.03 due to its larger rice, stickiness, and specific nutritional composition, while Japonica rice had the lowest oviposition rate, which is 0.43 due to its smaller size, less appealing physical features, and possible genetic differences. And a higher position rate in sticky rice clearly correlates towards a larger population of S. oryzae, resulting in faster population growth and higher intrinsic growth rates. And the recommendation, for my recommendation, in the future, studies on the oviposition rate of S. oryzae can be made extensively using rice varieties such as Basmati, Poni, Rumi, Keladi, and Borneo Highland rice that can be gathered in Malaysia. So new studies could further expand the focus on the damage created by S. oryzae in various more host types such as wheat, maize, sorghum, and barley, not only focus on rice grain only. So these are the references that I used in this slide. Thank you.